We are working on the bit by bit project from the YByte Python curriculum available at www.ybyte.in. Having seen a big picture view of bitwise operators, it's now time to start taking a deeper dive. We will start learning about these operators from this video. It turns out that in order to appreciate and understand bitwise operators in general, we will start with three basic building blocks, operators that work on a single bit. Now here we're looking at a single. This will in fact naturally lead into bitwise operators. So the three single bit operators we look at, kind of like the prerequisites or say the building blocks, will be an AND, OR, and an XOR. The good thing is that none of this is new for us, having been programming so much, and we can draw on our understanding of logical operators to understand this. Now, first, let's start with a single bit AND operator. Now, the way we draw it here is this logic gate called AND gate. Two inputs here. Now, these are both single bits, say 1 and 0, and a single output, which is again a single bit, say 1 or 0. Now, the way we capture, let's say, this functionality is using a truth table where we are just marking out, okay, what happens, when A is 0, B is 0, well, C is 0, A is 0, B is 1, C is 0, A is 1, C is B is 0, C is 0, and A is 1, 1, and this is 1. So what we notice is that, look, the output is 1 if and only if both the inputs are 1, which means this has to be 1, this has to be 1, then the output becomes 1. If either of them is 0, then the output is a 0. Good news, like I said, is that we have in fact already seen this in many ways. We can relate back to the logical operators that we have seen. For example, back in Scratch, we had done things like, in the knife game, if touching knife, let's say, and, touching color red. We have done this many times. If touching mouse pointer and let's say mouse down, right? So both the conditions have to be true. Then the output is true. So if we take one to be true, basically what we are saying is like, look, if this is true, then the output is true. Kind of like saying this is true, and hence the output is true. Likewise, if I can put a logical condition in Python, let's say if A is greater than 10, B is greater than 10, both have to be greater than 10 in order for the composite result to be seen as true. In fact, we see one more compare and contrast moment, one more analogy, I would say, from the Sports Hero project, where we looked at the intersection, players who have won Wimbledon, players who have won French Open, and this intersection is the players who have won Wimbledon, who have also won French Open. So one Wimbledon is true, one French Open is true. Hence, both of these are true. This is like an AND gate. So intersection here is really like an AND gate. Like I said, both inputs must be true for the output to be true. Moving forward, next we have the OR gate. Now, OR operator or say OR gate, again, A and B are single bits. It's drawn, let's say this is the customary symbol for the OR gate. A, B leading to a C. Again, the truth table is very interesting. Basically, if both are 0, then the output is 0. But if anyone or both, so basically if anyone is true, then output is 1. So essentially this, again, we can relate back to our, let's say our programming that we have been learning so far. I could have conditions like if capital of India is Delhi or New Delhi. Either of them can be true, and that is correct. If A is greater than 10 or B greater than 10, so A could be 15, B is 5 is also fine. A is 15, B is, let's say, 21 is also fine, because either of these conditions must be true. Again, from the Sports Heroes project, an OR gate is kind of like a union. So this or this, of course, it includes the scenario where there's an overlap, which means both of these are true. That's why you see 1 1 is resulting in 1. The important point to keep in mind is that if, look, any one of these is 1, then the output will be a 1. In fact, on that note, in an AND gate, if any one of this is 0, the output will be 0. It doesn't matter what the other other value is. Moving forward, in an XOR gate. Now, XOR is represented with an OR gate, with this extra line. So that's an XOR gate in logic. Now, again, the truth table is very interesting. You notice that if A and B are 0, 0 respectively, C is 0. If A and B are 1, 1 respectively, C is also 0. Which means that C becomes 1 if these two are different, which means 1 is 0, 1 is 1. It could be A being 1, it could be B being 1. The other one must be 0, because if both are 0 or both are 1, well, that becomes a false. In fact, interesting analogy of this comes from the Sports Heroes project, the symmetric difference operation. Remember, we wanted players who have won, let's say, the Wimbledon or the French Open, but not both. So, Wimbledon is 1, French Open is 0. French Open is 1, Wimbledon is 0. In this case, both would have been 1. That's not what we want. In these outer cases, both would have been 0. That's not what we want, right? So again, output is 1 when one of the inputs, but not both are 1. So that's an XOR gate. Again, take a moment to absorb this because this is the basis. This is the fundamental. In fact, these are also basic building blocks of digital electronics, for those of you who are interested to explore in future. Now, having learned these basics, we will now see how bitwise operators are formed by applying these on every bit of let's say, two numbers. We'll see that for the next video onwards. But I hope this has been interesting to you. In general, our approach is to build activities to understand concepts, and that is what we are doing here as well. Look at our website, www.yby, because we learn Python programming by doing fun activities like we are doing for the bitwise operators in this project. Take care. Thank you so much. Bye bye.